Under certain situations, it will approximate the binomial distribution using a normal curve. Imagine that we have a situation where n, our number of trials, is 5, and our probability of success, p, is 0.66. If we want to find the mean and standard deviation of the distribution, of the binomial distribution formed by this information here, with n equal 5 and p equal 0.6, the way you would do that is using these two formulas below. The mean is simply n times p. And really what that's talking about is the expected value, what you would expect to get if you took a sample. If you sample 5 people and the probability is roughly 2/3, you'd expect to get, somewhere between 3 and 4 people. And in fact, if you take 5 times 0.66, you end up with 3.3. So that would be how you would find the mean of a binomial distribution. Standard deviation is a little bit more complicated. It says the square root of n times p times 1 minus p. And really all that's saying is if p is the probability of success, 1 minus p is the probability of failure. So it's the number of people in your sample times the probability of success times the probability of failure. And you square root that. So we have 5 times our probability of success times our probability of failure, which you could either just type in your calculator as 1 minus p, or you could do the math first and get 5 times 0.66 times 0.34. We would take out our calculator and do that. 5 times 0.66 times 0.34. In my case, everything goes under the square root symbol in my calculator. If you need to use parentheses in yours, just watch out for that. And we're going to get 1.05 or 1.059 as our standard deviation. Now we're going to use this information here that we just calculated to help us in actually solving a normal curve problem, because now we have a mean and a standard deviation. So let's find the probability that x is less than 2. We sketch our normal curve as we always like to do when we have these types of problems. Always going to have roughly the same shape with our mean in the middle and then one standard deviation out about this far each direction. I could label it, but I want to get in the habit of using my z-score or t-score right away. In this case, it's a regular normal distribution, so it's going to be a z-score. And the first thing I want to do is translate this 2 right here into a z-score so I can plot it on my standard normal curve. So I'm going to take 2, subtract the mean, 3.3, and divide it by the standard deviation of 1.059. And just to refresh your memory, that came from the formula for a z-score, where z is equal to x minus mu divided by sigma, the standard deviation. So we take these values here, negative 1.3 divided by 1.059, oops, 1.059, and that's going to be negative 1.228. So that value right here is our z-score. And negative 1 point something, that's going to be on our standard normal curve. This is 0. This is negative 1. Negative 1.228 is going to be somewhere right around here. And what we want to know is what is the probability that x is less than this value. So we want to find the area under the curve that corresponds to x being less than 2, or translated into a z-score, negative 1.228. So to find area under the normal curve, we use the normal CDF function, and we have our left bound and our right bound that we type into that. So normal CDF, left side here goes on forever, so we pick some very negative number, such as negative 1,000. And then we stop here. Our right side happens right at our z-score. negative 1.228. And again, as a refresher here, we go to second vars for our distribution. Normal CDF is the second one down. And we're going to type in our two z-score values that we have, negative 1,000 and negative 1.228. If you hit enter, you're going to get your probability. So the area under the curve is 0.110 if we round it off to 3 decimals. And that's our answer. The probability that x is less than 2 is going to be 0.110.